Hello, welcome to Evidence and Reasons for the Christian Faith or Examining Evolution, whichever you happen to be watching this on. I'm here with Sal Cordova, who's been spent a considerable time doing very nerdy stuff in physics, and he's going to share with us some of the problems with the Big Bang, and I'm going to ask him questions.
Well, thank you for having me on. It's been quite a journey. Just a little intro about myself. I had accepted the Big Bang since I was in junior high school. By the time I was in graduate school in physics at Johns Hopkins, I had very, very serious doubts, and I said it wouldn't surprise me if it fell apart. I've heard professors at my universities, either quietly or quite openly, say they don't believe in the Big Bang, and that definitely got my notice. And also the graduate students, and then kind of the whispers, quote unquote, in the hall, so to speak. It's like, yeah, I'm kind of skeptical of this. And so I'm going to be sharing some of that today. And that's just a little brief about my background. Most people know me as a biologist. I'm really not. I'm an engineer that ended up getting retreaded in physics. And a lot of the physics that I studied was to help was the sort of physics that they would teach engineers who were building space probes at the Applied Physics Lab at Johns Hopkins University.
Okay, so when your professors expressed skepticism about the Big Bang, what were their problems with it?
Well, there was a cosmology statement that was organized in, I think, like 2004, 2005. Number of professors signed it, and it articulated better than I can articulate what their problems are. Their fundamental problems were that there were a lot of fudge factors that were needed to make it work. That was kind of the biggest thing. And I, there are just numerous things, and we'll probably talk about that. But there were just general anecdotes saying, that we might wake up someday and say, this is all wrong. And that's kind of the headlines we're get hints of it in the headlines recently, especially the James Webb Telescope, but then some other experiments that have been happening. So it's not just my professors, there are graduate students that were saying, Sal, we kind of, among us, we're kind of hearing that the Big Bang it's a failed model. And yet the popular press and the people building the space probes and investing maybe hundreds of millions of dollars in building all this instrumentation are just advocating and say, we're probing the beginning of the universe and all the details. And yet I'd hear a different story kind of in the, kind of behind quote unquote closed doors. But then occasionally some professors would come out right out and say it, that we have these fudge factors of dark matter, dark energy, inflation, the inflation field. Now, these are technical terms, but I think instinctively we would want the Big Bang Theory to have some agreement with everyday physics experience. And so the idea of expanding space is just we just don't measure it, and we don't detect dark matter. It's just very unsettling. And there are a number of unsettling other things that we can get into. But I think you phrased it well, and you were actually quoting your sister. The idea that all the galaxies, all the stars we see could emerge from a speck probably smaller than the head of a needle. That doesn't agree with everyday physics. That this is physics we are not acquainted with. Now, granted, we have to make an extrapolation, and we do a lot of that in physics. But at some point, you have to just kind of give a little pause and say, that's pretty radical. And if you're going to make an extraordinary claim, maybe it would help if you had some extraordinary evidence. Right now, we have a lot of extrapolation. And so at the very least, I think one's entitled to be skeptical.
Well, yeah, the paper that you gave me was by Michael Disney, who is a well respected astrophysicist. And what he was talking about is the main problem with the Big Bang is that we have when we have a theory that we're working with or a hypothesis that we're working with, we always want our observations, like the observational evidence, to be much more or outweigh the free parameters that we have to insert to make it work. And he said, the problem with the Big Bang is that we have totally done the opposite. We only have two observations that the entire thing is resting on, and that is the cosmic background cosmic microwave background radiation and the redshift. And so from those two observations that tend to support the Big Bang, then we've added and continued to add more and more free parameters or hypothetical entities to make this thing work. And I believe he listed 17 um, free parameters that have had to be inserted to keep the Big Bang afloat. Those are free parameters that we have no observational evidence for, such as dark matter, dark energy, like you mentioned. He also mentioned something called seeds, which is sort of like lumpy stuff that would have had to, help the galaxies and stuff form. And all of these things, and even he mentioned, and this is maybe the first question I have for you, he mentioned also that the cosmological constant is also a free parameter. And this is something that I've heard that cosmological constant quite a bit, but like he mentioned that as one of these things that is like we actually don't know what this, he mentioned it as a free parameter. So I wanted to ask you, what is your understanding of the cosmological constant, and is that something that people should believe in? What's the status of that right now?
Okay, you're asking some really hard questions, and I may have to ask a little liberty to actually Google a few things just to make sure I'm not misleading, saying something wrong and misleading the hearers.
Mm-hmm.
So you use some terms that I think would be helpful to kind of put in a little bit less nerdy, slightly less nerdy terms. Let's look at the history of geocentrism. It made a lot of predictions. The idea of geocentrism is the universe orbited the sun, orbited the Earth. The Earth was the center of the universe, and the rest of the universe orbited it. So they were actually, with the geocentric model, able to predict eclipses, the seasons. And you're like, well, look at all the predictions. Look at all the successful predictions it's making. And then anything else that is problematic, you add what they call an epicycle. So like there is retrograde motion that we were seeing, the funny motion of the planets, which we now know the planets in the solar system. And you could just say, okay, if we just assume that the universe orbits around the Earth, then we can build any sort of epicycle and fix our model. And so when you talk about the free parameters, that's what's troubling Michael Disney. It's like, okay, anytime you have something that's a little bit problematic for you, you just put in a new free parameter. Let us call it an epicycle, figuratively speaking. And that's what he finds bothersome. Whereas now that we have a real theory that the sun is pretty much approximately the center of the solar system, for practical purposes, we can assume that, and that the planets in the solar system orbit, you don't have all these free parameters are gone. No more epicycles. The theory resolves to very simple physics, celestial mechanics. And so now we explain at least the motion, not necessarily the origin of the solar system, but the motion of the planets, etc. And so that's, I'm trying to kind of boil it down, compare it to historical development. So the Big Bang could be totally wrong and still make kind of a few good predictions. And then you'll say, well, look at all the other ones it's making, but those are kind of like epicycle predictions. They're, you can make up whatever you want and say it satisfies it. And that would include things like inflation fields, dark matter, dark energy. So now with the cosmological constant, a little background, and if you'll permit me to Google just to make a, if I get this right.
Yeah, while you're doing that, I'll just say I'll put the link to the open letter that you talked about that was signed by 3 of your professors. And I will also put the link to that paper by Michael Disney. And keep in mind, actually, the paper itself is, I think it's at least 15 years old. So it's, it was from a while ago, but
It was
it's
prophetic.
just
It
as
was
true.
prophetic.
Yeah, it's just as true now. In fact, more true, because as I'm sure we're going to get into, as we've had more discoveries in the recent JWST uh, observations of the galaxies, and things are getting worse and worse for the Big Bang. And so, anyway, but did you find what you wanted to find on the
Yes.
cosmological constant?
Okay.
Okay.
So if I may just briefly share my screen so you know that I'm not.
Sure.
So Wikipedia is open source. Now, the only, this isn't peer reviewed, but it quotes what is considered like, um, so mainstream that it'll be an encyclopedia article. But so you have the cosmological constant. And let me just point out a variety of values here. Let's see. Predict. Let me just read this paragraph here. And you don't have to understand all the details, just focus on the final sentence. Depending on the Planck energy cutoff and other factors, the quantum vacuum energy contribution to the effective cosmological constant is calculated to be as little as 50 and as much as 120 orders of magnitude greater than observed. A state of affairs described by physicists as the largest discrepancy between theory and experiment in all of science, and the worst possible and the worst theoretical prediction in the history of physics. I mean, it doesn't get much
Wow.
better than that. And
Now,
I just wanted to make sure I was coding it right, because even I sometimes in disbelief. Now, readers of that article will say, well, look, they have another fix to this later on. If you read the article, it's like, yeah, how many times have I heard that before, that someone has come up with concocted some theory to plug a gap, and then later on you find out that gap also fails. You have even worse problems. So let's just say this is not settled. If we want to be like, not to be kind of overhyping and just be a little bit more circumspect, let's just say it's fair to say a lot of people think this is the cosmological constant, the worst theoretical prediction in the history of physics. Wow. And a little backstory again. In 2012, I believe, while I was finishing up my last year of school, it was announced Johns Hopkins won the Nobel. We had a researcher from Johns Hopkins that won the Nobel Prize in chemistry, and another one in physics. The one in physics was Adam Rees, and he had been working on the cosmological constant. He gave a presentation after he won the Nobel Prize, one that was actually scheduled. He didn't even know, but he was just going to talk about his work, and it turned out great because he just won the Nobel Prize and he's sharing it. And he said, okay, the figure I came up with doesn't agree. It's off by all these orders of magnitude. So even he, the Nobel Prize winner, was up there saying there's a big discrepancy, but that's not my job. My job is to make these measurements. I had the privilege of meeting him in a reception and shaking his hand. But I felt a little sad. I said, what if I was thinking in the back of my mind, he's a great guy, obviously brilliant and capable, but what if he's wrong? What if that discrepancy, even he admitted to, is telling him something's amiss? So that was 10 years ago, and I don't know that this has been resolved.
Okay, now that brings me to my next question, because now, from what I understand, the cosmological constant, what it is, it's an attempt to account for like the ability of space to expand and not to collapse. Like there's like some kind, there needs to be something there that would stop basically the matter in the universe from either completely flying apart or from collapsing in on itself. And so that cosmological constant is supposed to be the thing that is like something in there that's like keeping it in place but unknown. Is that
Okay,
right?
I've got to tell you, this is so hard. The way that I understood the cosmological constant was in my
Okay.
book on general relativity.
Okay.
And so I may totally get this. Okay, so there's a cosmological constant in general relativity, and it's all been postulated there. And then there's a cosmological constant we can apply to the Big Bang. So if we, and so to the viewers there, what I'm about to say may not agree with the way you understand it.
Wait, you're
But
saying there's two different things? Because I thought like the cosmological constant, like Einstein came up with it, but he said it was his biggest mistake.
okay, page 188.
Okay.
Hang on. I, I'm sorry, you kind of caught me a little flat-footed here. Okay, so it is
I've been nerding out, right, Sal? I've been nerding out.
okay. Uh, yes. All right. So Einstein field equation. All right. So let me.
We can edit all this out. We're going to edit all this out. We're going to have you looking like a superstar. You're going to have all the answers right away. Don't worry about it.
Okay. So let me just share it the way. Okay. So regarding the cosmological constant. So let's start with general relativity and then its role. So general relativity is the theory of acceleration and gravity, the way it affects things, and we don't need to get there. But you see this thing here in this equation, this upside down triangle, it's called a lambda.
Yeah.
All right, so this, when I studied general relativity, we just assumed this term didn't exist. It was zero, which made all the equations so nice. And so it was debated where this thing should be there or not. And so suffice to say, it was kind of a theoretical thing. And they said, well, maybe should we include it or not? And so they said, well, maybe some of the things in the Big Bang, if we start to see that the expansion is accelerating, maybe we should put that term in there. And so there's some things in quantum mechanics that might suggest that you add this term, and then also observations in the Big Bang. So that's what it is. It is we were making either observations or theoretical predictions from the other field of physics known as quantum mechanics, whether this term should exist and what value do we assign to it. Mm-hmm. So quantum mechanics would give one figure, and then Dr. Reese and others who were observing and working from the assumption of the Big Bang got another figure. And there was a huge discrepancy between what quantum mechanics predicted and what they observed based on the Big Bang. And we don't know what value should be here. When I was going through school, we just assumed it was zero. And as a student, we liked that because it was one less thing to worry about. And it made the math so much nicer if you didn't have to throw in that term. So that's my understanding. Now, if they're interested readers that say Sal didn't quite get it right, that's fine. I would welcome the feedback. This stuff is really hard. It's not like easy biology. This stuff is incredibly hard, and I know because my professors get tripped up. Sometimes you'll ask them like, they'll be like, I don't know. It's amazing. So that's kind of what the cosmological constant is. So there you got your taste of general relativity right there. And but
you're saying like we actually still like it is, as Michael Disney was describing, it's one of those like hypothetical parameters that we're using to support the theory, but we actually don't know that this is even exists.
Right. Well, we'll put it this way: we're throwing a value in there that may not be right.
Mm-hmm.
That might be the better way to characterize it. We still don't know if that term, the cosmological constant, should even be in general relativity. So, Big Bang will provide its number, but then if the Big Bang's wrong, what do you do then? So, if if another theory is predicting a different number and the Big Bang's given another, what are you going to give priority to? And this is the question. So do we have an experiment or observation that can resolve the issue? So going back to geocentrism, what ended up happening is we had observations that say, at what point do you have so many observations and the only way you could deal with them is to add more of these artificial fixes? At what point do you just give up and say, let's adopt a simpler theory?
Yeah.
And what if we just, what if people said, this is the best we have, so let's just keep persisting with it? And that would have been the wrong way to approach this. So we could be at that stage now where it's like, okay, do we just start from scratch? Or is it better to just say, we don't know for sure? We don't know for sure. And then that may open the door to actually finding the correct solution.
Yes. Okay. So there's so many directions I want to go with this. So
well,
I'm
okay,
going to try to stay organized.
Can we just tie up the loose end here?
Yes.
Remember that last sentence. The worst theoretical prediction in the history of physics. Just
yes. Okay, and let's tie up this segment a bit, regarding the free parameters that have been added over and over again to keep the Big Bang afloat. And so what Michael Disney was saying about it is that that outweighs greatly these bits of observational evidence that we have for the Big Bang, but it's stacked so high, and that is not a good model when you have to have all those free parameters and they greatly outweigh the observational evidence. That's a good indicator that your model is wrong, because you should have more and more observational evidence. And so the Big Bang model is getting more and more away from observational reality.
Well, and it's very subtle, because when you add a free parameter, you can claim you made a successful prediction. So the epicycles actually did make successful predictions. Mm-hmm. But is it correct when you can just make anything up and it doesn't agree with any physics that you are discovering? So that's what Michael Disney is having problems with. Is they gave Adam Rees, Saul Perlmutter, and someone else the Nobel Prize for something that could be just, on sand. It could be based on circular reasoning, and it's subtle enough that you won't notice the circular reasoning involved, and it will look like it's based on observation, and it looks like it makes a great prediction. And so what Michael Disney is saying is that he's able to formally see. That's what he was exceptional at. He could actually formally say, no, you haven't closed all the loops on this. This is not a good theory. This is like geocentrism, because you could have an anomaly out there that's going to overturn what you just said. And this is, again, stacked so high. So, as I read it, I said, you have to be really good, and I'm not that good, to be able to formally say, no, we've not shown the Big Bang is true to the exclusion of other possibilities. I think that's the way to say it. That's the problem with the free parameter. When you have data that will start to destroy all the competing theories, then you've kind of, you've sealed up all the gaps. And that's what he's, basically saying. We've not sealed all the problems. So what you want to have, going back to our, the earlier cosmology, when you have the solar system, you don't have free parameters. Everything's tight. every measurement
Right.
that you make, it is so precise. That's why we can send space probes throughout the solar system. And he's saying we don't have that. So I'm just, the reason I'm kind of being vague about this rather than get in the formalities. One, as I said, I'm not as good as Michael Disney to actually formally demonstrate this. And it is so deep in the weeds. I think it'd be too much for you and I, and certainly the viewers to weigh into it. So, that's why I kind of like that quote, the worst prediction in the history of physics. That's
Yeah. Now, but let's talk about the actual evidence for the Big Bang, and I would just like to talk about some of the other possibilities. Saying, okay, assuming that the Big Bang is wrong, what could these be? What could these observations mean? And or let's just say, are they good? You know, evidence for the Big Bang. So one of them that's given is cosmic microwave background radiation, right?
radiation.
So
The
this
redshift, I
was
think, is
discovered, and this is one that I think people point to, the CMB. Well, let's start with CMB, then we go to Redshift. But the CMB, it was discovered in 1965, and some people I have told me this was predicted. We predicted that the Big Bang, that there would be this cosmic, background radiation. We predicted it, and then we found it. And then in other sources, I saw that it was like, actually, this was an accidental discovery. We accidentally discovered it, and then we applied it to the Big Bang. So, do you know what is actually the truth about that?
I have heard two accounts of this.
Mm-hmm.
Going back again to geocentrism predicted a lot of things. Doesn't mean that it's right. So that's the first thing to know. So then the
Right.
second thing is I've heard what you just said, is that they're conflicting accounts of how accurate that prediction was, whether it had to be revised to make it look like they made a successful prediction when it wasn't. It may have been off by a few degrees. There may be, but let's back up. I mean, let's hypothetically say that in principle, maybe not practical, but we say, there might be an experiment we could conduct in principle, but it might not be practical within our lifetime. What if the microwave background radiation is local, like it's maybe just surrounding our local area, kind of like a fog? I mean, how do you know? How do you know that the fog is? I mean, if you look outside on a foggy day, if you didn't have any other experience on clear days, you'd say, oh, the universe is just full of fog, right? Until it
Yeah. Now,
clears. And so
what is it about the background radiation that they're saying makes it good evidence for the Big Bang?
that was covered in my cosmology book here.
Mm-hmm.
And it never really made that much. They said that was a relic from the explosion, quote unquote explosion. It's not really an explosion. And that was actually reasonable that some people had predicted a relic,
Mm-hmm.
that you would have this energy out there, that it would bathe space. But what if the figure was wrong? So I think, let me just put it this way. I don't think it. I would feel, if I were on the other side as a Big Bang apologist, I would feel uncomfortable saying this was an absolute prediction, because you have these conflicting accounts. And so let me just leave it at that, because I think there are more substantive areas that we can touch on that may falsify this. But going back to let's say, if this was okay, let's just grant for the sake of argument this was a prediction. How could this be falsified in principle? Maybe not practically, but in principle. What if we had observations from way, way, way outside of the solar system, and you realize, oh, this was a local phenomenon? That would falsify it. Right now, we're assuming that it's bathing the whole universe. We don't absolutely know that. And where in Big Bang Theory did they say that there's an axis of evil, this anomaly that seems to coincide with the solar plane? Where was that predicted? I mean, if you're going to be fair about it, it's like, oh, the Big Bang predicted we're going to have this anomaly on the solar plane that they call the axis of evil. I'm like, okay,
Yeah.
I'm just like, people began to be a little skeptical at this point, and I think rightly so, that when you start to see these anomalies in the quote unquote background radiation that coincide with the solar system, you begin to think, oh, maybe this could be a local phenomenon. I mean, if it can be so easily perturbed by our solar system plane, there's something should be kind of troubling. So
Yes, and for those who are watching who haven't heard of this, this is, the idea about the cosmic background radiation is that when we first observed it, it looked completely smooth. But as we've done more observations, and by the way, smooth and isotropic is what we would expect from the remnants of the Big Bang. And so that was what was expected. But as we've looked at it in more depth, there's like fluctuations that have been observed. And those fluctuations happen to correspond with the elliptical plane of our solar system, which is very strange if this is radiation that's coming from the edge of the universe, that these fluctuations would happen to correspond to the elliptical plane that our solar system is on. That's very odd. So this is an issue, and it's called the axis of evil in cosmology. So
if you want to read this, this is a beautiful, just the first few couple sentences or the whole paragraph.
sure. The axis of evil is a name given to the apparent correlation between the plane of the solar system and aspects of the cosmic microwave background. It gives the plane of the solar system and hence the location of Earth a greater significance than might be expected by chance, a result which has been claimed to be evidence of a departure from the Copernican principle as assumed in the concordance model. I don't
How
really
about
understand that.
how's that for obfuscation? A result has been claimed as to be evidence against the Big Bang, but we have to kind of say, oh, evidence against the Copernican principle or the concordance. Just come on, go
What
out
does
and
that,
say it.
what do they mean by that? The Copernican principle as
Okay,
assumed
the
in the
Copernican
concordance.
principle. Okay, um, unfortunately, like a lot of terms, it's evolved over time what it really means. Okay, in the present day, okay, this is not what it necessarily meant in the past, but in the present day, the Copernican principle means we're not in any special place. We're
Mhm.
not in any special place. We have no significance. But if our solar plane, okay, let's say that the microwave background does have this anomaly throughout all the cosmos. Why would the solar plane accidentally just kind of align with it? That would mean we're kind of in a special solar system that just happened to have its planets orbiting that it aligns with this axis of evil. What are the odds of that? And that's what they were saying. But if you want to take it further, you could say, well, maybe this isn't a cosmic phenomenon at all if it can be perturbed by our planets in the solar system. Um, and again, so
Like maybe it's not out there at the edges of the universe. It is right. It's like something closer in our
right.
galaxy, in our solar system.
So okay, if it is universal, then we are special in God's sight because He made the solar plane kind of. I mean, this is quoting my secular professor. He used that term, we're special in God's sight. And he's not particularly religious, but he said, we have all these coincidences. This isn't, we could kind of put that, any violation of that Copernican principle where we have this funny coincidence as something that seems unnatural. It's like, we could accept that we just happen to have something happen to make us more special than the rest of the universe. And a lot of scientists find that philosophically troubling because that's very close to being a miracle. So, and that's why the Copernican principle, it, in the modern meaning of it, not necessarily the historical, it has a lot of metaphysical baggage attached to it, because any violation of the Copernican principle, it suggests we are so special, and that at what point does being special mean that it's a miracle, a miracle of the supernatural? So, right there in that Wikipedia entry, you can't you can't read it, accept the cosmic microwave background radiation, and not start stumbling upon deep metaphysical questions right there. Or the Big Bang is wrong, and the microwave background radiation is therefore possibly a fiction. It could be a local microwave radiation, local microwave background rather than cosmic. So this is again what I was saying about the fog. If the only day you lived was the day where you saw the fog, you might, and you're unsophisticated, you'd say, oh, the fog is cosmological. It's like, well, how logical is that?
Yeah. Okay, now, but fix my thinking if I'm wrong. To me, it's like, okay, you guys found some radiation in space. I don't even care if it's not local. Okay, you found it at the edge of the universe. Wow. How does that um support the idea that all this stuff was squished into it? Couldn't there be another explanation? Like, isn't it even just
Yes.
equally as likely that there's another explanation for like random radiation in the universe?
Yes.
I
Yes,
okay,
exactly.
okay,
Back to the
okay.
geocentric model. When you make an observation and a prediction, it has to be to the exclusion of the other models. What geocentrism failed to do is it could never do that. And it had a lot of anomalies if they were paying attention to say, no, this just is not square. We keep getting observations. We can either keep assuming it's right and putting these epicycles, or maybe we just abandon it and try something else. And yeah, so good point.
Okay.
Even if there were all this radiation throughout space, and to that point, some theories have suggested this is going into what they call black body radiation. So if you heat like a piece of metal up, you'll see it turn red and then all these other colors. That's because the heat gives a certain amount of frequency of photons, and it's actually a distribution, and it has a particular what they call the black body distribution. It's kind of complicated. Max Planck won a Nobel Prize in association with that. He was just staring at ovens all day and figuring this out. Now, the significance of that is, can you think of things that create heat out in space? Like, say, stars? And if the stars start to hit certain things, like, you might have some plasmas out there or whatever, it can create a exactly as you say, at about one calculation was it's about 3 degrees. Now, I've heard arguments back and forth. Okay, I'm not saying I'm right, but it's like exactly what you say. It's not to the exclusion of other possibilities. And I've heard seen some calculations saying, yeah, if we do it this way, we might have enough energy to create that just based on the starlight available, but we don't really necessarily have a mechanism to kind of smooth it out and make it a black body. But it's able to provide that amount of energy if we could somehow find a mechanism to convert it to that approximately 3 degrees above absolute zero. So it's not, it's exactly as you say, Rebecca. It's a prediction that's not to the exclusion of other explanations. And that's what free parameters and all that Michael, in addition to, or maybe capturing the sense of what Michael Disney is saying, we're not able to come up with these numbers to the exclusion of other possibilities. So that's really good that you caught that. Could be to the edge of the universe. That's excellent.
Okay, so now let's go to Redshift, because I think this is probably the observation that, it has the strongest evidence for the Big Bang. And so we've observed this redshift in galaxies and objects distance from us, and that gives us the impression that they're moving away, right? And so then I guess if you extrapolate backwards, well, then maybe they all came together at one point. But to me, just because, okay, if they are moving away right now, and I have to ask you a lot of questions about that because now I'm in serious doubt about that. But I was accepting that before because even Michael Disney says he thinks there's good observational evidence for, the expansion of the universe, right? But even if there is an expansion of the universe, does that, why would we necessarily extrapolate that all the way to like coming together at a single point?
Okay.
Like, is
This
there a
is
reason for that?
yes, there's okay. Again, it's accepted because it has scored, just like a sporting event, sometimes the opponent can score some home runs, and some things, the Big Bang's not all bad. That's why it's persisted. If it were all bad, it probably wouldn't continue. So this is a chance to then talk about redshift and electromagnetic radiation, and there's some caveats. So instinctively, like when you're hearing a train come at you and then move away, you're hearing shift in the frequencies of sound. We call those Doppler shifts. Now, with electromagnetic radiation, it's not exactly. It's very close. So when they have, in particularly for cosmological, but it just suffice to say it's close. The idea is close. So when the police have a radar gun on you and he has a trap and he's just waiting for someone to pass him, the radar beam that he sends out and then it bounces off you, it's we could say it's quote unquote Doppler shifted. It's not exactly, but that's close enough. Just like that train, you can tell when it's moving away from you. And if it's moving fast, you're going to have that stronger shift. So the radar beam is then quote unquote red shifted. So he knows the frequency.
Means the wavelengths are longer.
They're correct. So reasonably speaking, this says that if we see red shifts in the stars, that they must be moving away from us. So this is a very nice extrapolation. It's not bad science. It's actually pretty good science that we've verified. And if you get a speeding ticket, like I did once upon a time, 40 years ago, it's like, hey, those red shifts, that's not because I was moving away from you. There's some anomaly in your physics. And so it seems very powerful that it's a good explanation. So if it's moving away from you, then it suggests that it's expanding. So what are your options? If space is expanding, it had to start from a point where it was not expanded. And so the question is, okay, instinctively you'd say, well, I think a speck is too tiny. But fundamentally, you could say, okay, we don't have to start with a speck. It has to start from somewhere and give it whatever size, but it's expanding now. So the whole thing about it shrinking to a speck, I got to admit, that feels kind of uncomfortable. So you need some additional theories to help you build that. But the idea that it's expanding because you look farther, as you look out there, you see all these redshifted galaxies. That's instinctively either it's moving away or it's not. If it's not moving away, then you have to explain the redshift a different way. Does that sort of
now from what I understand, mainstream astrophysicists and like cosmologists, they accept this idea of the expansion of the universe. And so I've been listening to a lot of stuff by Eric Lerner, and he has some pretty very convincing reasons to not believe that the redshift is equal to expansion. And it's based on our observations from the Hubble Space Telescope, JWST, and other things as well. And in fact, I found my own that I was looking at. This wasn't even from Eric Lerner. I'm going to pull this up for you but anyway, but I'll pull that up in a minute because I don't want to get distracted from my main question.
Can we just back up a little bit?
Sure.
We could say, and there's some, I'm sure there's probably a model out there that says, okay, maybe we didn't expand out from a little tiny speck, but the galaxies are still moving away from us. So fundamentally, the redshift, if we interpret it as motion, just says it's moving away from us.
Right. So it doesn't necessarily mean that it started as a singularity. Okay. That's it.
Correct. So there is a subtlety there. And I just wanted to say, it's one layer more of inference that you have to add some assumptions to get to get to the idea of that starting of a speck. I mean, even though this would be, I guess, to a lot of scientists kind of like heretical, just to say, well, suddenly the universe appeared in full form, but then all the galaxies were just moving away from each other. I mean, that's hypothetically, that model would sort of work too. So, I'm just saying,
I mean, that would
strictly
be
speaking, it's not expanding space.
Yeah.
It is the galaxies moving away from us.
Right. But do you think redshift does mean expansion?
No. And there is one, before I get there, I know some of the very sophisticated crowd will say, look at all the time dilation predictions. There's a paper by Crawford. If I may just show it before we get into it, because I know some people are going to try to shoot me down. Dilation. And I sent this to you. You can.
Yes, I tried to read this one. I couldn't understand it. So you'll have to just.
Okay. So, hang on. Let me give the citation first before you jump, before the audience, the Big Bang fans jump all over me. So let me just show it here, because I know certain individuals will just be arguing, said, no, we have definite proof, like Ned Wright and someone named Adrian Malott in Kansas. He's a professor of physics, and he introduced me. But there is a citation by D.F. Crawford. You can get it on the Cornell archive. It has since been published in a peer-reviewed journal. And but this is like what they call a preprint of it. And it basically says all that stuff with time dilation was falsified. Maybe I could just show a graph.
Wait, explain the time dilation.
Can I do that later? Because I want to go back to the redshift, and I'll get back to it. But this.
Wait a minute. But you haven't. Okay. I'll just be patient.
I just threw that out as a place marker, just so people will say, Sal, you're ignoring this. Like, no.
Okay.
But to be able to be succinct and not go to every important rabbit trails. And in this case, these are important rabbit trails, but let's just start with the basics. So if I'm out there and I'm trying to dispute the ticket with my police state trooper friend who's saying, we caught you speeding, sir. My radar gun picked that up. And I'll say, well, the redshift doesn't necessarily mean I was moving away from you. That wouldn't really fly. Okay, so it's a very reasonable assumption to say if you see redshift, it means something's moving away from you. Now, there are a couple problems with this. The first is really basic, and it may involve the problems with certain objects like quasars. We don't, in the case of the police radar gun, the manufacturer knows what frequency the radar signal is being sent out. We actually don't know what the source signal is coming out of a quasar. We have to kind of guess. And, we have certain patterns of, the spectral bands and so forth. But YP Varshney said, this is, it's not as easy as you think, because he's thrown random examples and people say this is redshifted and it's not. And suffice to say, I wouldn't say this is a ubiquitous problem, but you have to be a little cautious. There are problems with quasars. They may or may not be as redshifted as we think. YP Varshney has said that. But let's assume that it is redshifted. Why don't we just extrapolate what happened with the police radar gun? So there are a couple of problems with that. The police radar gun is only traveling, that radar signal is only traveling, say, a few,
miles or something.
Yeah, not even miles. Okay, so they'll say, oh, how about we use this in fighter planes or whatever, or to predict Doppler shifts over like hundreds of miles. It's like, okay, fair enough. But it could be that over millions of miles, or billions, or bazillion miles, there's enough of a shift that starts to add up. And then also, what if it's passing through plasma? And that's important because there's a lot of what we call plasma in space, charged particles. If it's interacting with a charged particle, like say an electron, we do know for a fact that under certain conditions, certain photons will be redshifted if it hits an electron. That's called Compton scattering. Now that's not a good explanation for the redshift because it'll blur, this is a known fact. But I'm just saying there's interactions with matter over large scale distances we know could cause redshift. But the really powerful thing, and I can't believe that this was lost on people for so long, and let me bring this up. Let's see, Pioneer 6 anomaly. Pioneer 6, and see if I can get it. Okay. 1974, prestigious scientific journal Nature. Perturbations of Pioneer 6 telemetry signal during solar occultation. And rather than get deep into this, what they found out is because we know Pioneer 6 is sending out a 23 megahertz signal. So this is like the police radar gun. Now it passes through the solar corona, which has these plasmas, free electron plasmas, and it's redshifted. It's redshifted. This ought to put a lot of pause. And this was a paper in 1974. It's redshifted. And as I read this, I said, guys, we need to have a big time out here, because now we have something that, it may not overturn my speeding ticket, but this can overturn the claim of redshift implying something is moving away. So they had to do a lot of mathematics to establish, okay, the redshift was not because the Pioneer space probe was moving away from us. We accounted for things like gravitational redshifting and all the effects of general relativity, the motion of the Earth, the motion of the sun, etc. And it's like this signal is really redshifted by the plasma. 1974, and it kind of was forgotten. And then we have this article here, and it's in the Journal of, this is High Energy Physics, Gravitation, and Cosmology. So the researcher Trinchera also reanalyzed this in great detail, and I sent this to Rebecca, and I can't believe she read through it. I mean, this is an agonizing paper.
I read it. I don't understand everything that I'm reading, but I did read it.
This was so thorough, and I'm like, you want to see good science? This is good science.
I know, right? I saw those. I was like, oh, who spent their life making these diagrams and stuff? This is real. This is nerdy science stuff. And I just thank you, whoever did that. Who's the name on that paper? I just want to thank that person.
Alessandro Trinchera.
That's wonderful. Thank you, Alessandro. That's
Thank you,
beautiful.
Alessandro. Okay, so people are saying, well, he's not a real known researcher. I'm just like, okay, why don't you go back to 1974 to that Nature paper? You got a prestigious journal basically saying the same thing, but Trinchera kind of revisited it. I felt, honestly, this Trinchera's paper, what came out 2021? That was only last year. But I said, I would feel better if I found other researchers that kind of reinforce what he's saying. And then I only stumbled on it the last few months, even after I read this, that it was actually someone else had independently arrived at the same thing. But Trinchera went a little further to try to explain it in terms of the mechanics. He has an explanation in terms of what he calls Wigner crystals. And Wigner crystals were only confirmed to exist in the last year also. And
Okay, we're there to the Wigner crystals because
okay,
this is another thing I do not understand. So but we really do know that Wigner crystals exist. Like it's real 100%. This isn't dark matter type stuff. This is like real.
yes, and I covered this.
I watched
Okay,
your show, but I was like, what is a Wigner crystal? Like this was never discussed. I don't understand what it is.
okay. So Eugene
Very
Wigner,
simply, one sentence. What is a Wigner
crystal
crystal?
made of electrons.
Okay.
Crystal made of, and just so people don't, I mean, just so people know that I'm not making this up, you can just flash the screen there, and you'll see it. It says Wigner crystals. Eugene Wigner won the Nobel Prize for his work on quantum mechanics, and he predicted the existence of these. They're basically like an electron. It's a crystal that's made of electrons. That's not exactly right, but it's close. So
Okay.
Trinchera suggested this is an explanation, but that being said, that may not be the right explanation. I have my doubts. But what is
Okay.
not in doubt is that the signal was redshifted when it passed through a plasma. And guess what? There's tons of plasma in space. It's just a lot more dilute than what you have in the solar corona. So maybe it's just passing through a million miles of concentrated plasma. But what if you have a bazillion miles of dilute plasma? You get the same effect, hypothetically. Now,
Hmm.
obviously, again, going back to the police radar gun, uh, his signal does not travel far enough for these effects to be measured. That's why experimentally it's so difficult to demonstrate this. But there has been one experiment where redshift happened in the laboratory because it passed through a plasma. And if you'd like me to get you that,
Yeah.
okay.
Yeah. And while you're pulling it up, I'll just say I have another thank you to Eric Lerner, who he wrote The Big Bang Never Happened. And he wrote that, I think, 30 years ago. And he's still really, talking about how the weakness of this idea of the Big Bang. And he really talks about it as a myth and shows how much it contradicts observational evidence. So thank you to Eric Lerner. And
Thank you, Eric.
I appreciated his book so much and his videos and stuff online. And so I'm really just glad
Okay.
that there's somebody. When I read his book and when I see the way that he has persevered, I'm thankful that somebody would stand up for so long, you know, against this model,
Yeah.
despite just extreme opposition, and it just warmed my heart.
Yes. Okay. So this one, intrinsic plasma redshift, now reproduced in the laboratory, a discussion in terms of the new tired light by Lyndon Ashmore. That is really more of a commentary on an actual experiment. But if you go to this, you'll get to the actual experiment where they're able to redshift with lasers in a plasma environment. Now, again, I'm not saying this is, you can take that down now. I'm not saying that this is whatever caused the redshift in the lab is what causes it out in space. But I'm just saying, we are being, I think, given all the ways we could redshift things, other than an object moving, and certainly more than just expanding space. I think at the very least we need to do a timeout and say, maybe we're being a little premature.
Yeah.
And especially if we start finding anomalies like the biggest failed prediction in the history of physics, it's like I think we have to kind of do a timeout. So we'll get to Crawford's paper, which I cited earlier for the big skeptics out there, the Big Bang apologists. So you did a big thank you to Eric Lerner. Can I do a big thank you to James Trefle and the 3 professors at my university? So James Trefle was my professor at George Mason, but there are also 3 others who signed a letter that Eric Lerner helped compose. This is cosmologystatement.org. And if you want to put that up while I talk about, cosmology, that letter that was signed. And I know that the names
it'll be linked in the description. People can
okay. You'll see in that link description 3 professors from George Mason: Minas Kafatos, MIT PhD, Center of Earth and Space Observation, Sisur and Malibuka Roy, 2 others, 3 of them from my university. And then there's kind of a 4th, maybe 3, and he's kind of not really the 4th, but a half. This would be a great opportunity to can I read you this passage?
Yeah, please.
So my professor of supplemental quantum mechanics, James Trefle, he was a pioneer of dark matter theory. And he had this to say. So this is going to be about 2 pages long. In the winter of he says it's subtitled, "What Are the Odds?" In the winter and spring of 1986, I had the privilege of spending a sabbatical leave working with a paleontology group at the University of Chicago. I was working on the problem of mass extinction, that is, what killed the dinosaurs, and the visit gave me a chance to get acquainted with David Raup, the leader of the group. Dave has been described as the most brilliant paleontologist in the world, an evaluation that, after a period as his collaborator, I think is well-deserved. He is also one of those rare individuals who get tremendous enjoyment from everything they do. He loves to question things that everyone else accepts without question, a trait that I suspect has a lot to do with his success as a scientist. He is also a terrific card player, as I learned to my sorrow at some late-night poker sessions, and spent some of his spare time at his personal computer trying to find a way to beat the system at blackjack. I mentioned these things as background to what I want to tell you about, something that happened during my visit with the group, where we were in Dave's office discussing something or other when he turned to me and asked, right out of the blue, what are the odds that the Big Bang is correct? That brought me up short, as you can imagine. My first impulse was to say, of course it's correct, but I suspected he'd ask me how I knew, so I paused. The more I thought about the question, the more fragments of memory floated into my mind. I recalled a bag lunch in a prestigious physics department when a prominent senior member of the faculty, I wouldn't dream of embarrassing him by mentioning his name, said that he often thought of leaving a sealed envelope to be opened 50 years after his death. In the envelope would be predictions about the way certain scientific controversies would turn out. At the top of the list would be the prediction that the interpretation of the redshift as evidence for universal expansion would turn out to be wrong, the Big Bang. This book was written, copyright 1988. Okay, so this is 1988. He often thought of leaving a sealed envelope to be opened 50 years after his death. In the envelope would be predictions about the way certain scientific controversies would turn out. At the top of the list would be the prediction that the interpretation of the redshift as evidence for a universal expansion would turn out to be wrong. I mean, okay, so here's my professor, And this is a book he's written. I took the class in 2004. And that's just going to make an impression on a student. And then you hear the other professors at the university openly expressing skepticism, enjoying siding with Eric Lerner. And then you hear the graduate students, you hear other professors, kind of the whispers, and you're just like, I think this thing could be wrong. And and then you read and you pursue. So go on, Rebecca.
Well, now you said Dr. Trefl that you just read from his book, he pioneered dark matter. So did he eventually say, no, dark matter is not real? I mean,
okay,
what did he come out with?
Okay. So it's been a long time since I took his class, 2004, and that I've had an interaction. Whether he's changed his mind or not, and sorry, Dr. Trefl, if I'm misrepresenting, I don't know what his current views are. Now, he did give a table of the probability of certain aspects of the Big Bang being right, and he kind of lists, some things he found problematic. And so I don't know what his views are. So when I said he's kind of half there, maybe not even half, maybe he's, maybe a 10% skeptic, maybe 90% he believes, but he's holding out skepticism. But there was another, I got to just point this out that just kind of struck me, because after I read that chapter, the very next chapter said this: 5 reasons why galaxies can't exist. And he describes why the Big Bang is incompatible with galaxies. I
really want to hear this, please.
Okay, 5 reasons why galaxies can't exist.
Wait, are you going to read it or summarize it for us?
I'll read it because he's a great writer. Okay. First, he starts with a quote. It says, "The progress report is there is no progress." And that is Nick Kosarok. He's a Montana snowplow driver during the blizzard of 1985. It's just kind of funny. He opens with that. He says, "We can summarize the modern view of the universe in 2 brief statements. First, the universe has been expanding ever since it was formed, and in the process has evolved from simple to complex structures. Second, the visible matter in the universe is organized hierarchically. The stars group together into galaxies, galaxies into clusters, and clusters into superclusters. The problem we face then is to understand how a universe whose evolution is dominated by the first statement, that is expanding space, could become one of those whose structure is described by the second, that is galaxies and galaxy clusters and hierarchy." So right there, even in that paragraph, he's saying, the galaxies shouldn't be there in an expanding universe. The problem of explaining the existence of galaxies has proved to be one of the thorniest in cosmology. By all rights, they just shouldn't be there, yet there they sit. It's hard to convey the depth of frustration that this simple fact induces among scientists. Time after time, new developments have come along, and it has seemed that the problem was solved. Each time the solution turned soft, new problems developed, and we were right back where we started. And there it is.
But what are the other reasons galaxies shouldn't exist? He said 5. Now I want to hear the other 4. I heard 1.
No. He gave the general. Now he has the 5 specific reasons based on it. All right. Now, okay. Reason 1, galaxies could not have formed before atoms. And he gives, now this is a 1988 book. Okay. So some guys, so to be fair to Dr. Trefl, some of this may or may not have been addressed. Okay. Reason 2, galaxies haven't had enough time to form. Oh my goodness. Aren't we hearing that now with the James Webb telescope? Galaxies have not had enough time to form. Reason number 2 still holds. Reason 3, turbulence won't work either. I don't know. You need turbulence to make galaxies. I guess you could blow it apart. I'm not going to read the whole thing. Reason 3, galaxies haven't had time to form clusters. Oh boy, if Webb starts finding clusters back there, this is bad news. Okay, this problem would still hold. Reason 5, if radiation clumps with matter and matter clumps into galaxies, the cosmic microwave radiation comes out wrong. All right. So to be fair, 1988 book. I talked to him in 2004. He said, yeah, I think, the Big Bang's looking better now at the time. So he thought it improved, just to be fair to him. But, all sorts of other things are popping out. But I'm just saying, okay, as a student of science, and everyone's just admiring Dr. Trefil. In fact, he gave the exam a week early and he said, okay, the last class is optional. I'm not going to grade you on anything. Just come out if you want to hang out. Everyone came out. Most students would say, I want to take a break. They came out 9 o'clock in the morning to hear Dr. Trefil just hang out with us and, answer our questions. That's how revered he was. And I point that out. It's like, okay, here's this revered scientist and he's pointing this stuff out. What's a student of science going to think? Except to maybe start to hold out skepticism. That skepticism did not diminish throughout the years. It's only increased, and especially after last year, and especially the last few months, I'm just like, oh my goodness, I think this theory is in trouble.
Wow. So yeah, especially now, and since we're talking about the galaxies, maybe it's a good time to bring up the, well, first, I just want to say briefly, and maybe you can correct me if anything I'm saying is wrong, but in order for the Big Bang to work, we have to have like a bunch times more dark matter than we have baryonic matter. Is that right?
Oh my goodness. Now you're starting to talk to something I'm not.
Okay, no, that's fine.
So dark matter was there to.
You can't be an expert in dark matter because it doesn't exist. Because there's no observational evidence at all for dark matter. So there's no reason to believe in dark matter unless you desperately need your Big Bang model to work, right? I mean,
okay, so the first thing was dark matter, and by the way, Disney is an advocate of dark matter, ironically.
What? Really?
I think he wrote a book on dark matter. Okay, it wasn't exclusive to the Big Bang. We couldn't explain the spirals in the galaxies without dark matter. And there's all this thing with gravitation, how, if you didn't have the dark matter halo, the spiral arms would disappear over bazillion years or less, however many billion.
Evidence for young Earth, evidence for young universe.
So
you can either make up dark matter or you could just accept what the Bible says.
Are we going to edit that one out? Anyway, okay. So dark matter was proposed. It solved the problem of the spiral galaxies. In my cosmology book, there is some diagram in here that says, well, we kind of need it to fix some other things, and I'm sorry. That was part of the course that I probably was sleeping through, figuratively speaking. This was okay. This book was like this. It's just kind of more of the same that you're reading, all the stuff that you see me nerd out on. So it has a role in it. I think it has to be there to help form the galaxies and explain the spirals, and it has some role in the Big Bang. That's obviously why Dr. Trefil, he calls it the dark side of the universe, because he's talking about the dark matter solution. He's trying to solve the 5 problems, okay? The 5 problems that he articulated, and to be fair with him, he said, dark matter solves all this. Except, do we have any? Okay, can you wait? Can I get a clump of dark matter and weigh it? Okay, we're having a very hard time. They built they spent an ungodly amount of money building experiments to finally detect it. And they didn't detect it. What does that mean? Either the detector wasn't that good, or it doesn't exist, or dark matter doesn't exist. Right now it is an inference. And and all sorts of things have come up where when this experiment, these dark matter detectors failed, they're like, what are we going to do? Because they said if it exists, it's smaller than the electron or smaller than something. And they said our detector should have picked it up, but it didn't. And so maybe it doesn't exist. And what about dark energy? I mean, can you measure it? Can you make a laboratory experiment that measures expanding space? Now they'll say, well, these are too subtle for us to measure. Okay, that raises the issue of testability. If you have an entity you can't directly measure, you can still believe in it, but you begin to you can't hold out. You can't help but be a little skeptical when problems keep coming up, and you're not able to demonstrate that this stuff. You cannot use the laboratory to demonstrate that it actually exists. Now, granted, we're dealing with large stretches of space where the experiments might have to be conducted over a bazillion miles, and that may be the case, but we're still stuck with not having laboratory confirmation, and that's one is entitled to hold out skepticism. So that's the problem with dark matter. And then the dark energy, which I think they've equated, the Big Bang advocates have equated with dark energy with the cosmological constant. Remember, that's the biggest failed prediction in the history of physics. So there's some major problems here.
Yeah.
So see, dark matter, dark energy, and now we have this thing called inflation, where the matter that makes all the galaxies had to expand at thousands, millions, or a bazillion times the speed of light. The speed of light. It has to separate faster than the speed of light, and that should make someone feel uncomfortable. When you can just when I was sitting in cosmology class and this was being described to me, I almost fell out of my seat, and I said, I thought the idea, some of the ideas I hold were outrageous. I said, mine are no more outrageous than what you just said. You have no basis to assume that exists except to say you need it to say the Big Bang. The alternative that they began to propose, they said that does seem kind of outrageous. How about we invoke variable speed of light? And if you're thinking, I'm kidding, look it up on Wikipedia. This is, a lot of what I'm trying to say. The reason I've cited Wikipedia, I'm trying to say I'm not just pulling this out of the air. This is stuff people talk about that you don't hear in the popular science press because there's a certain narrative being pushed.
Right.
But if you're invoking variable speed of light, boy, all sorts of possibilities start to emerge as far as cosmological alternatives. So, and the inflation idea has been slowly, it's getting a lot of critics and being discredited. Nobel Prize winner recent Roger Penrose has come out against it. So, again, as a student of science that had heard this about the skepticism, every year it's gotten worse. It's like, what am I supposed to think? At some point, it kind of reassures you that maybe this is credible, that this is wrong.
Yeah. Well, okay. Speaking of, let's go to talking about, because we're talking about the problems with the redshift. If redshift is expansion, right? If redshift means expansion, then that causes a lot of problems in our observations. And so Eric Lerner, like I said, I've been looking at a lot of his stuff, and so this is some of the problems that he mentioned, and I want to talk through these with you and kind of compare it. But I first want to show you one that I found. This actually came from a lady, astrophysicist from Oxford. Her name is, hold on, Becky something. Anyway, this is from her YouTube channel, but she was talking, and she's a believer in the Big Bang, but she admits this crisis in cosmology where we have this problem where as we're trying to calculate the expansion rate of the universe, of the galaxies and things and the expansion rate. When we use cosmic CMB, cosmic microwave background, we get a different rate than if we calculate it from the supernova and the redshift using Cepheid variable stars. And so like this is a problem. And so this was one of the problems. She was hoping that the JWST, she made a video last year saying, I'm really excited about JWST because hopefully it's going to resolve this problem that we have, because we're getting two different expansion rates. And but actually JWST, it has reconfirmed this the same calculation that we're getting from the Cepheid variable star, because the Hubble Space Telescope put these Hubble telescope took pictures and got information, and we thought, so in her video she said one of two things has to be happening. Either our model is wrong, either the Big Bang model is wrong, or we have overcalculated for the brightness of these Cepheid variable stars. And so maybe there's a problem. Maybe there was another star overlapping and the Hubble didn't have as good instruments as JWST. Well, JWST information came out and reconfirmed Hubble, the Hubble calculation, JWST, totally right. So nothing has been resolved with this little problem here. So they're having a big problem calculating the expansion rate. And as some people may say, well, who cares? Okay, so what? They can't calculate the expansion rate. Well, how about if we just say maybe it's because there isn't an expansion rate. Maybe the problem is that you're using Redshift as you're using Redshift and thinking that it means expansion, where it's actually just correlates to distance, but it doesn't mean expansion. So what do you think about this, Sal?
First off, bravo to you. You totally out-nerded me on this one. I've never heard of Wendy Friedman. I've not studied it. So congratulations to you for digging this up. I'm so behind the times, Rebecca. I mean, you're ahead of me on the latest. I kind of have some of the basic stuff, but you're finding some cutting edge criticisms. This is great.
Cool. Thank you, Sal. Okay, well, now let's go back to Eric Lerner stuff, because I want to compare this, because a lot of people are criticizing Eric Lerner, and it's really incredibly frustrating to me, because I go on and I see this response to Eric Lerner by Professor Dave. Professor Dave with 2 million subscribers. And, all he does is insult Eric Lerner and insult, anyone who believes this stuff for, 10 minutes, and doesn't really address any of Eric Lerner's stuff. But this is the big problems here with these using the redshift, if you think of it as expansion, is when we observe these distant galaxies, like with JWST, we get absolutely ridiculous galaxies. So, this galaxy GHZ2 would have to be 14,000 times brighter for its volume than any other galaxy that we observe nearby. It would have to be.
Actually, that's 28,000. You divide 14,000 by 0.5, it's 28,000.
Oh, wait. Oh, okay. I think he already did the. Are you sure?
I'm pretty sure.
Okay. Anyway,
we could ask the aficionados, but look,
So,
14.
okay.
Look, okay, if it's 14,000, you're still off. Okay. That's like
But like,
getting half a cent when you're expecting $14,000. Okay, it's or 50 cents when you're expecting 14,000. It's a big discrepancy.
right.
So we don't have galaxies there, and I can try to explain this, and this is where I'm a little weak, but it also goes to Michael Disney's point about the Tolman test, the Tolman surface brightness test.
Mm-hmm.
Um, and so in my cosmology book here, it talked about when an object in expanding space, um, normally the brightness, there's something called the surface bright. There's something about the brightness that'll be the same with respect to, how big it is, no matter how far. If it follows a Euclidean non-expanding geometry, the farther away something is, it gets smaller, but the amount of brightness per area is should be constant. In an expanding universe, it drops off precipitously. So maybe rather than get technical,
Yes.
there's a very simple thing that Michael Disney said, and is beautiful. He
Yes.
said, the Tolman surface brightness test, when we were building the Hubble Space Telescope,
Mm-hmm.
the Big Bang advocates, and Disney was one of them, he said they were coming up to him and said, don't bother building stuff like, that can detect it, because all you're going to see is darkness. The Big Bang is going to say, you're going to just see blackness. You're not supposed to see it. He said, consider our surprise then when the photographs came and we were seeing all these things. So what they have to assume then is in order to account for that, they have to assume that these galaxies, the farther out you look, they had to be really, really small so that they could emit
Yes.
that much brightness per surface area to compensate. So either they're really, really small, or they're actually big in the redshift and space is not expanding. And that's what Lerner is pointing out. He said you can either assume that space is expanding, or that the redshift does not indicate expanding space. And if space is not
Yes.
expanding, then you don't get these crazily compressed galaxies. One that is, the volume brightness isn't, I can't tell you what that diameter, what that would translate into, but it's pretty small. Um, I haven't worked through the numbers, but the idea
Well,
is it
he
has to
says it
be
up here, the radius,
radius. Yeah.
6,000 parsecs. Okay, this is if there's no Big Bang. Okay, I mean, if we don't calculate redshift as expansion, but instead consider just redshift correlates with distance, right? If we do that, then this galaxy GHZ2 becomes like an average galaxy that we observe nearby. Okay, like basically average radius that we observe nearby of nearby galaxies, like known galaxies that we observe nearby, are very similar. If we take away all this Big Bang expansion calculations and we just do redshift corresponds to distance, then we have a very normal galaxy here, right?
Yes.
And
Exactly.
and if we have to calculate, if we have to do all the, if we have to consider that, okay, it's the that optical illusion where, hey, the light was closer to us when it left, and so now we've got to calculate that it's actually smaller, then we get these ridiculous sized galaxies. So it's 90 parsecs in radius, which we've never observed a galaxy anywhere close to that. So that's like a ridiculously small galaxy. And he goes on talking about how these are like impossible galaxies, like just impossibly small galaxies. And I looked this up. This is one of the problems mentioned in cosmology today is these dwarf galaxies. Okay, so this isn't just Eric Lerner saying this. This is a known problem in cosmology, and I even found, like I told you, I wanted to find, not just get it from a video by Eric Lerner, even though I think he seems like a trustworthy source to me, but I went and got it from the scientists who were putting out and getting the data about these galaxies. And this is a galaxy that has a redshift of like 13 or something like that. And they're actually 4 galaxies that they're comparing. And they said these galaxies have median star formation rates comparable to the present Milky Way, despite them being more than 100 times less massive. So they're using these Big Bang calculations and they're getting these like ridiculous size galaxies.
Yep. Yep. Exactly. And I'd like to share something. There is a problem with the link to Setterfield's website, but I was able to retrieve the document anyway. If I could just share a little bit of it,
Sure.
because, all right, forget what Professor Dave says anyway. He says the stupidest stuff, uh, about abiogenesis and his cosmology. It's like, okay, you're getting someone who's not even, he doesn't even have a Bachelor of Science degree. He has a Bachelor of Arts degree. And he's pontificating about stuff. Sorry, I just had to take that little jab at Farina. But Setterfield's article, you may have some problems. There's some security issues with his website. If you just click advanced options and just load, you'll be able to get it. Problems of the Big Bang from the James Webb Telescope. And I'm just going to quote, he does a good job of just quoting scientists. He said, one scientist said, no one was expecting anything like this, says Michael Boylan Colchin of University of Texas, Austin's. Galaxies are exploding out of the woodwork, says Rachel Somerville of Flatiron Institute. This is way outside of the box of what models were predicting. Okay, another failed prediction. And here, okay, I'll quote this one here. Right now, I find myself lying awake at 3 a.m, says Allison Kirkpatrick, an astronomer at the University of Kansas in Lawrence, and wondering if everything I've done is wrong. And by the way, I mentioned Adrian Malot's name. He was a professor there, and he was advocating the Big Bang, criticizing kind of my skepticism. And here's someone right from his school now saying, I'm wondering if everything I've done is wrong. I mean, this is so, the thing about Lerner is people would like to just criticize him. And I'm just like, guys, you can pick on him. Lerner's just reporting on what other people have said. So, don't blame it on Lerner. You might want to try to deal with the data and what other scientists are having to acknowledge. And I've told you, even as I matriculated through school, I could hear it. I could hear it in the hallways. I could hear it in discussions with fellow students. I'm just saying Lerner is just a very good reporter. He's also a scientist on this, but let's just distill what is coming out from researchers themselves. This isn't what you would want to find from a healthy theory. This is another great article if one wants to read. And at some point, I hope to get back to Crawford's article on time dilation and the redshift.
Okay, yeah, we will. Okay, we can get back to that, but let's finish up this talk about the problem with the JWST, the observations that have been made, because another observation that was supposed to be, we were supposed to see galaxies colliding out at that distance, because that was how the galaxies were supposed to get bigger. And so we didn't observe that. We observed too many galaxies out there, and we observed mature galaxies out there, like elliptical galaxies and spiral galaxies. And those weren't even supposed to be out there because they're not supposed to be any galaxies like that And this is where I need to ask you a question. But anyway, because we're looking out at that distance, we're seeing like, 500 million years after the Big Bang. And there wasn't supposed to be any, especially not any mature galaxies out there, right? So now there are mature galaxies out there. And I've been hearing like talk about, okay, like I could only hear Lerner talking about this, and I wanted another verification. But he was talking about how, Sal, are you listening to me? Because I'm going to ask you a question. This is a question for you.
I'm actually looking up galaxy evolution because now you're throwing out terms I'm not familiar with, and I was desperately trying to catch up so I could answer your question. So I already know that I won't be able to. You have out nerded me again. But I am somewhat familiar with what I was looking for was a choice quote from the Wikipedia article that deals with the hypothesis of merging. And I don't recall that I ever read it in my cosmology class. There was something here that was talking about it, but please go on. I wasn't trying to be rude. I actually was anticipating your question. I was desperately trying to answer it, what I anticipated your punchline would be.
Okay, well, what Lerner is also talking about is the problem that these galaxies that we're observing, if we like do the calculations, they are actually older than the Big Bang itself. And so I was trying to figure out more about that and find a different source. And this is really what I could find out. Like the most distant one that we observed is supposed to be like 330 million years after the Big Bang. I can tell you're not listening to me. You're reading.
No, I'm half listening.
It's not enough. You gotta fully listen. Okay.
All right. Okay. My full attention now.
We'll pause it. We'll pause the thing so we can edit it. I mean, you know what I'm saying? Like we can edit out the part where you look.
So you said something about 300 million years, right?
Yep. Yes. So I was trying to figure out, where did Lerner get the idea that then those galaxies would have to be older than the Big Bang. And what I could find out for myself, and I wanted to see if this is correct, because I don't know if it's correct. But when I looked up like elliptical galaxies, it said like the age of elliptical galaxies, they're like between 7 billion and 10 billion years old.
Okay.
So then, like, if it's between 7 and 10 billion years old, and we're seeing the light from 330 million years after the Big Bang, then those do have to be older than the Big Bang, right?
Yes, that's a problem. Okay, so.
Okay.
Can you show my?
Am I doing the thinking
yes,
right on that?
Yes.
Because this gets really confusing.
Okay.
With the time
Now, that being said, you out-nerded me on this, and I had to desperately look up the reference. So let me point the readers. This is good because I want to show when Rebecca and I are not pulling this out of the air. We're just trying to show this is so mainstream. It's in Wikipedia if you want to look it up, and you can look up all the references. So look up this. And this is what I was desperately looking at: galaxy formation and evolution. And there's a section on elliptical galaxies. Elliptical galaxies have to form by mergers with pre-existing galaxies. So first thing is you have to have a galaxy that's already formed, and that takes time. And let's see. Here it is. Astronomers now see elliptical galaxies as some of the most evolved systems in the universe. That means oldest. Oldest. So if you got that 7 billion year number, that is consistent with the Wikipedia article. And so at least this one has been written before someone has revised it in light of the James Webb Telescope. So qualitatively, yes, I think you understood it. And because I was seeing that prior to even our discussion, like say even, when the James Webb stuff was coming out, I said, let me just look at galaxy evolution. You've actually studied it more in depth than I have, but at least I wanted to be acquainted. So my role in here is kind of saying, I think you've kind of the sanity check here is that I think you're reading it correctly.
Yeah.
Yeah.
So, in the other problems that Lerner mentions with the Big Bang is failed predictions, like many failed predictions. So, like, it's not just that they're making up hypothetical entities; they're also failing so many predictions, and then they have to like make a new parameter or whatever, because of the failed prediction. So,
or a promissory note, maybe not even a parameter. Let's say, oh, we'll figure it out in the future, just like abiogenesis.
okay, now can you talk about, do you know about some of those failed predictions? Because obviously these things about galaxies are failed. So failed prediction, they thought they were going to see no galaxies with the Hubble telescope. They did, and that was then JWST, even worse because they're even older. Then they didn't see the collisions they wanted to see, so they don't know how galaxies are forming that way. So that's failed prediction. They weren't expecting the maturity of the galaxies, and that they're there just Milky Way style galaxies where they're not supposed to be. Those are 4 failed predictions. Lerner mentioned some other ones. One of them has to do with helium, but I don't remember if it was like there's too much helium or there's not enough helium. Do you know?
No.
Okay.
See, and you're pointing out a problem. Every time there's a failed prediction, it's like, no, it's not failed yet, because there's another possibility to explain it. And so, but I mean, like the Tolman surface brightness test, look at what they're doing to solve the Tolman surface brightness test. They're just saying, oh, we need a new model of galaxy evolution where we have these little teeny tiny galaxies we don't explain yet, but there, the problem solved. Another epicycle, so to speak, figuratively speaking. So, is it really failed? It's, it's like, it certainly would look like it's failed, given the assumptions we have. So it's like, okay, let's just revise our assumptions. So we fix it by making new assumptions, not by actual, it's exactly what you said. It's kind of like a free parameter. You just change your set of assumptions. And, the big one is the inflation model. Let's just assume that galaxy quantities of matter can be separated faster than the speed of light. Problem is solved. When you can invoke such kind of new principles of physics that have no confirmation except your, a faith belief, you're basically, this is like free parameters of the gaps reasoning, promissory notes of the gaps type reasoning, epicycles of the gaps type reasoning. I mean, that's what it's looking like to me. When we look at the solar system, the heliocentric model, all the gaps disappeared. So many of, to explain the motion, not the origin, but the motion of the solar system, the gaps totally disappeared. You don't want to have to be filling the gaps by making more gaps, free parameters of the gaps reasoning, or promissory notes of the gaps reasoning. And that's the situation we have.
Right. So with all of this, are there any good reasons to believe in the Big Bang?
It was for a long time, and that was the time dilation and the redshift. I found that very, very problematic. When Adrian Malott, University of Kansas at Lawrence, and the same one, later that we have that Allison there who was saying she's up at 3 a.m. he said, look at this one, Sal. And he knew I was somewhat of a student of physics. I said, yeah, I think you're kind of right. He was quoting Ned Wright. So the idea is, and I demonstrated this on my channel, and if I may brag a little bit, before I bring this up, do you have anything that you saw that is good evidence for the Big Bang while I'm looking at this? In
No,
anything?
no, not at all. But not at all. But, since so many people believe this, I want to give it the benefit of the doubt. I want to understand what is so compelling about this. And so far, the
Okay.
answer that I'm realizing is that people are committed to the model, and a lot of smart people have pushed the model and believed in the model, and so that's kind of created this system here where everybody's committed to it. So
Okay. Now, you normally and commendably want me to be succinct. Unfortunately, this time dilation thing is going to be a little thick, and to do it justice, I'm going to need a little bit more time. So I'm just going to
okay,
roll up my
but just
sleeves
try
here.
to make sure, just try not to lose me,
All
because
right,
I
stop me.
just
Stop me
try
if
to
it's
do it as succinct as you can so that I can
okay.
understand and that other people can understand.
All right, so we're going to start with basic physics. So the operation of the modern world, you have generators, you have radios, and it's represented by Maxwell's equations. If you could show my screen, and you can take Maxwell's equations and you could do something, a derivation that I had to do in graduate school, which I elaborated on in my channel, and I'm so proud of it. I did this derivation starting from basic electromagnetic theory that tells you how your generators and microwave ovens work. Those are called Maxwell's equations. If you take Maxwell's equations, you can do a derivation like this ugly one here. Actually, to me, it's beautiful. Look at all the nice Christmassy colors. And this shows that when you move faster, the time dilation implies it relates to something called the twin paradox. So this took me hours to put together from electromagnetic theory. It shows that the faster you move, your clock slows down. So let's look at this. I had an illustration here, and this is going to relate to the Big Bang. See if okay, so let's say it's called the twin paradox. The twin paradox is if you have two twins, let's say they're fraternal, and the girl takes off in her spaceship, and she's flying really, really fast. What'll happen is if she flies to 99.999999996% the speed of light, a day for her will be like 1,000 years for her twin brother. So we could either say time flows differently. I would prefer to say her clock slows down. Her age, she ages slower. Now, I went through the trouble of showing electromagnetic theory and those derivations. That was a prediction. We've actually been able to confirm those predictions with atomic clocks that we flew in airplanes. Now in satellites, your GPS won't work if we don't make correction for the speed of the satellite flying in space, because its clocks slow down because of the speed. And they all, and the gravitational effects too that make it do the opposite. But fundamentally, if something is moving fast, it ages slower. That's kind of the...
Yeah.
Okay, so I just wanted to show there's a lot of math, a lot of experiments that prove this. So what they said is if the Big Bang is true, objects that are flying faster away from us, they ought to at least appear to age slower. So the higher the redshift, the slower it ages. Part of it is the dilation, this dilation effect, and then some other effects because of expanding space, etc. And it's a very complicated equation that they show in books like this, my cosmology book. So that's a prediction. So how could we possibly tell if something is aging slower? So you could take this down just briefly, and I'm going to bring another slide up shortly. It's like, okay, let's say we have a supernova that we kind of know the parameters of how long. Okay, we'll observe supernovas near us and say, okay, if it's about this size and it radiates this color, we'll just kind of average things out and we'll figure out, okay, we expect it to kind of explode and then kind of decay. They call it decay of a light curve. The intensity. It'll happen over this amount of time. So if we see a supernova far out there and it's redshifted, we ought to see that it ages slower. And so they did all these studies that said, hey, we confirmed the time dilation just as predicted by both relativity and expanding space. This phenomenon, the twin paradox phenomenon, plus some extra things. It's kind of complicated. We confirmed it. This is proof that redshift is cosmological expansion. And I 2004, I was just like, oh my goodness, I think Adrienne Mallant, you got a point. I can't run away from that. Well, this goes to Crawford paper, and I referenced it earlier because I knew some people would be jumping all over me, and I have so many windows open, I have to kind of close them so I could find the paper now. Oh, here it is. I got the paper up now. So let me explain this diagram. What he found out was, let me just give an example from casino. If you say, hey, every time I go to the casino, I win every game. Well, what happens if you do your accounting and you just erase every time you lost? You call that cherry picking, right? You can make a case by cherry picking. What Crawford found out was that if space is expanding, and they used a particular criteria for picking the supernova that they picked, you end up cherry picking data points along here. So all of these papers that supposedly demonstrated time dilation, he found a subtle, not deliberate, probably just a subtle circular reasoning where all the points that were used in the study actually assumed what they were trying to prove, and they ended up picking only the supernova that confirmed what they were predisposed to believe. We call that confirmation bias, but here it wasn't really so deliberate or nefarious. It took him some work to figure that out. But he said if he surveyed all the other supernovas, he'd see the absence of time dilation. Hence, he argues forcefully space is not expanding. He had a hard time publishing this through peer review. He's a respected astronomer in Australia. He's not, okay, if I may comment, Eric Lerner has been throughout his life, and again, thank you, Eric Lerner, because you persevered despite being not an academic. It didn't matter that you didn't have as many credentials as other people. You kept telling it the way you saw it. Thank you. But people like Crawford, people like Michael Disney are respected astronomers. Crawford came up with this. He said, there's no time dilation in this. And he's not the only one. There was a further study by Hawkins that studied quasars. He said, the quasars are supposed to pulsate at certain rates, maybe aperiodically, but, it's just like when you're driving on a road at slow speed, you don't get periodic bumps, but you could tell when you're moving faster because the bumps are more frequent. The greater the redshift, he found it didn't cause any change in the frequency of these quasar blips. So there's no.
Wait, is that here in this paper or is that in something else?
Edward Hawkins, quasar time dilation. Let me see if I could find it. Yeah, Mike. This was. He's published a lot, but he did get a. He got a peer-reviewed publication, and he talked about time dilation and quasar variability, and so this was a failed prediction. And he tries to be fair, he cited some possible explanations for it, but again, more epicycles. This is not. It's like, why do we
Oh,
have to?
so he's not trying, he's a believer in the Big Bang. He was trying to show that there was a, a
He was trying to be
yeah.
fair, and he
Uh-huh.
said it's not my problem, but this is the result I got. And
Right.
he said, um, another situation where one would expect to see a time dilation is the light curves of quasars, which are at cosmological distance and vary on timescales of years. A number of groups have looked for time dilation in quasar light curves, but so far it seems fair to say no convincing detection has been made. So this is another paper for you
Wow.
in addition to Crawford. So I think maybe Disney or Crawford or Hawkins, they're citing each other, but this is like, okay, you know, so me in 2004, Adrian Malot's confronting me with the supposed evidence of time dilation in the redshifts. And I said, yeah, I think you're right. You know, I can't run away from that. And then this starts coming out, these two studies, and I'm just like, holy smokes, time out. And then, you know, even then that wasn't convincing, but these last set of experiments in 2021, where the redshift was confirmed to have occurred through solar plasmas, I said, you've got to do a big timeout. This is too big. So would you like me to send you this in an email?
Oh, yes, that would be wonderful. Yeah.
So let me unshare my screen here. And, you know, if you have some, I'm going to try to half listen to you while I'm sending this to you in an email. So I apologize. I'm not trying to be rude, Rebecca. I
Oh,
really am
no,
trying
you're
to
not.
address your
No, that's
question.
fine. I was just gonna just talk about one of the I found just a little paragraph about the um contradicted predictions of the Big Bang. So, with regard to the light elements, lithium and helium, the prediction for the Big Bang was any super hot explosion throughout the universe, like the Big Bang, would have generated a certain small amount of the light element lithium and a large amount of helium. Yet, as astronomers have observed older and older stars, the amount of lithium observed has gotten less and less, and in the oldest stars is less than 1/10 of the predicted level. The oldest stars near to us have less than half the amount of helium predicted. However, well understood fusion processes in stars and reactions initiated by cosmic rays have accurately predicted the the correct amounts of these and other light elements. So, if we, understand, instead of the Big Bang Theory, if we, you know, consider these other processes, then we can have more, more accurate predictions for the lighter elements than the Big Bang provided. And then the other one was like this antimatter. I don't know if you know anything about this, Sal, but the antimatter matter annihilation. Like, um, so, okay. Well, maybe you should explain it.
No, no, no. Go ahead.
Well, the idea is that, any type of like intense radiation like the Big Bang would cause like antimatter and matter to be produced, right? And then they would annihilate each other. So we shouldn't really have the matter that we have, um, because it should have all been wiped out. And so that's kind of one of the things that dark matter fixes, as far as I understand it. But I could be wrong about that.
I'm not that familiar, and so I would say as we start talking about the elements, we're starting to get we focused. I think, by the way, the order that we did think. I don't know if this is your opinion, but I think the way this conversation has gone so far, we've really hit the really big things. I mean, hit
Yes.
them hard. Um, we're now starting to go kind of into things that I think are less, we really, I think, just like what Michael Disney would say, you
Yeah.
try to hit the pillar at the bottom. This stuff about the nucleosynthesis and all, maybe 30 years ago, this was, or however many decades, it's like maybe that was kind of the few things we had, maybe critics of the Big Bang could cite. But now the evidence for like the James Webb Telescope and then the Redshift experiments and then the time dilation stuff, I'm just like, I think we've hit it so hard on the big matters that I wouldn't focus
Don't
on.
even go there.
Yeah,
Yeah.
that's where I would say I think we've covered succinct. And then also you made some good points about muting some things. Like, for example, the cosmic microwave background radiation could have other explanations.
Mhm.
Or we could have galaxies moving apart that don't involve expanding space or starting from a speck. I mean, you could still invoke redshift as a measure of velocity, but it doesn't mean we began from a speck. You're having to lay one more assumption in there. But since we're talking about matter, there is a problem in the origination of atoms and the periodic table. There's no question of that problem. And I know that nucleosynthesis, they claim these things of R processes and P processes. I'm not that familiar, but it's questionable whether it works. So you have the Big Bang, and then you have to have energy suddenly converting into to matter. You have to have some process. I mean, because you obviously can't have ordinary matter coming from that little speck that she said. It has to expand and then start to kind of figuratively speaking, crystallize into these forms of matter. And first it'll all be probably like, hydrogen, just protons and electrons. You have hydrogen, and then the hydrogen has to synthesize into the heavier elements all the way up to uranium and beyond. The Big Bang doesn't explain that very well. It's you have to hope you have other things like big bad supernova, and then even then it may not be sufficient. And plus, some of these exotic matter, exotic stars, and even then it doesn't work. So, because the alternative is matter just kind of popped into existence in that state. That, if we're going to be free parameters of the gaps thing, I can suggest all sorts of other gaps. I mean, they're just certain. Okay, I got to point out, certain gaps are unacceptable. The way you fill the gap has to be a certain kind of gap. It can't be one that kind of looks like it was specially made. Okay, that's specially made in place. That's the kind of gap you will not. But you got to admit, if you fill that gap that way, why shouldn't it work? And you you may be able to have testable predictions where if you use those gap filling things, everything actually does start to work beautifully. Just like if you assume a ready-made life, everything works well. I have argued, why don't we just accept the ready-made universe? I mean, wouldn't all your paradoxes just kind of disappear? I mean, if you're going to be in the mode of filling everything with gaps, but you'll only be selective about what gaps you'll be willing to entertain, I think that's problematic. Why don't you I just said, okay, why don't you just accept the ready-made universe? Why is that uncomfortable? Wouldn't that fill
I
all
know
the
why
gaps?
it's uncomfortable.
I like a ready-made universe. What's wrong with that? Just start with it kind of like the way it is now. I mean, if you're going to use gaps and things that are unexplained, okay, let's look at the inflation model. It's unverifiable, it's unprovable, undetectable, and yet it's been considered science. As for all we know, it was just inflation of the gaps, another free parameter of the gaps, or another promissory note of the gaps that has no possibility of verification.
Yeah.
So if you're going to accept inflation where you have matter being separated at thousands, maybe millions of times the speed of light. And I've, some people have said, well, effectively infinity, if for some models, it's like you could practically just, okay, it's going to expand at this infinite rate and then just stop, basically relatively, it's still moving, but it kind of stops, relatively speaking. It's like, well, what's different then than just saying, why don't you just have a ready-made universe?
Yeah.
You can't verify that either, except it may agree with some observations. So that's, you wouldn't need dark matter because then you have the spiral galaxies, right? It's just kind of made that way.
Yeah. Okay. Wait, Sal, I wanted to ask you about one more thing before we close, because this was, I guess I was trying to look this up because this is something that Eric Lerner said, but he was saying that like it was predicted that there couldn't be anything more than a certain like distance across. And I can't remember the number right now. It might have been a billion light years. And like that the Big Bang predicted that there couldn't be anything. I don't think you're listening to me.
I am.
Because you're reading. What are you reading? Are you trying to look this
I'm
up?
looking at nucleosynthesis. I want.
Okay.
Okay, I'm sorry. Okay, all right. You have my full attention now. You're so perceptive. It's like if I don't look you in the eye, you can say, Sal, you're not listening to me. Okay.
No,
All
but
right.
it's true though, right? You were reading. You couldn't really pay attention to what I was saying.
Okay.
You don't really know what I was saying.
You caught me. Nothing escapes you, Rebecca. Okay.
Okay, so but basically that the Big Bang at different times, like back in the 60s, 70s, they were saying there couldn't be anything that would exist that like any kind of structure that could be like bigger than, I think that thing was a billion light years, right? Like nothing could be more than a billion light years across or something. And then now we've found all these like superstructures like that are like 3 billion light years across. And by the way, I might just be making up that 1 billion, but that's what I wanted to ask you. Do you remember this?
It was in Treffel's book. And this is actually the first time these fields are so, they're so broad and you could actually miss things, but there are, he says there's a structure problem with the universe, and he tries to say that dark matter might solve it. So we have these ideas where you have galaxies organized in clusters, but then the clusters form strings. You don't have kind of like this kind of homogeneous mass. If you ever do you ever see like, I forgot, these plasma balls where you have the electrical currents and they're like lightning bolts coming out of it? That's the concentration of the galaxies. It looks like a lightning had struck it. That's why, not that I agree with these electric universe theories, but you got to admit it kind of looks like that. You have these strings out there, and it looks like it's like that doesn't seem right. And so I don't know if that's what Lerner was referring to, but Treffel is acknowledging this is kind of problematic. You kind of want something a little more homogeneous. This is kind of unsettling that they're organized in these strings that look like a lightning bolts out of your plasma ball. I mean, yes, why would that be?
I think that was the different thing, but I think this one has to do with the fact that like these structures don't have time to form. And, even under like the inflationary model, because, at first we had to do the inflation thing because how did the galaxies, come together? Because, they couldn't be, I don't know. I think I'm getting too tired and confused now.
Can I just show you if I could show my screen here? I got a conceptual picture of this galactic string. And I don't, I'm sorry, you out nerded me on that one. this isn't what we should be expecting to see, but we do, and that's troubling.
Wow. Yeah.
Yeah, kind of like that plasma ball. So, what was I? There was something I wanted to say about that string. Oh yes, before I forget, if the Big Bang is false, there is one troubling anomaly. Now, Luke Barnes, I had a conversation with him online, and I talked to him about the fingers of God effect. Because the way these structures are laid out, if we don't assume the Big Bang, we have, in some of the stuff, we have kind of a problem where we have all these strings or these structures, and they're kind of all pointing toward Earth. And we call that the fingers of God. And I don't know enough, but Halton Arp was saying, what do we do? You know, it's like the fingers of God are pointing, and it's so funny. Let me see, just so you know, I'm not making this up. It's a cosmological term that, let's see, Halton Arp, fingers of God. Halton Arp was Edwin Hubble's assistant, and he was at the Max Planck Institute of Research. So he was against the Big Bang, but he's a respected astronomer. And let me see if I can get this, because it's really kind of funny. So, oh yeah. The fingers of God are pointing at you. And this is okay. A website observing this is, what do you think this cluster is? In fact, they are forced to say it as it is a structure that I would compare to a great sausage stretching out from us toward the outer reaches of the universe. And I think this is Halton Arp. Let me make sure if this is Halton Arp. Yes, Halton Arp said this. The miraculous aspect is the sausage is pointing directly at us. But perhaps an even stranger aspect is that the far end would be receding from us at an appreciable fraction of the speed of light. Quick, the mustard. The cluster elongations toward the observer have been noticed in other regions of the sky, causing some inquietude, being dubbed fingers of God. The reason for unease is obvious. The fingers are pointing to the conclusion that we live in some special place in the universe. Very anti-Copernican. The fingers of God are pointing at you. So I don't know how the Big Bang could explain that.
Wow. Very cool. Well, thank you so much, Sal. This has been awesome.
It has been a lot of fun.
All right, I'm going to stop the recording. Bye.